Alright, hey guys, what's going on? So today we are going to be talking about the Bianchi identities. And also we're going to be covering what the Bianchi identities mean in terms of the Einstein curvature tensor. So, without further ado, make sure to hit that like and subscribe button. If you want to support the channel, make sure to go into my Patreon page where you can make a very small donation of just $3, and you can also get notes to these videos. So with that being said, let's get right into the topic. Okay, so the Bianchi identities. We're going to start with the Bianchi identities, and then we're going to talk about the Einstein tensor and what the Bianchi identities really mean in terms of that tensor. And then we're going to start talking about what we're going to, the next topic in this, which is going to now really focus on the physics of things, okay? The next video is going to be talking about the stress energy momentum tensor and how the physics of things really gets put into this. But let's talk about the Bianchi identities. So we're going to start off with recalling the Riemann curvature tensor. This is something we've sort of belabored ourselves with already a couple of times in my tensor calculus playlist and in this playlist. So in a local inertial reference frame, the affine connection will go to zero, meaning that the covariant derivative gets reduced down to a regular derivative, and the Riemann curvature tensor becomes something that looks like this. Okay? So essentially in a local inertial reference frame, the affine connection is going to go to zero. That's why these guys go to zero, but the derivatives don't necessarily go to zero. Okay? So we keep the derivatives, and this is what our Riemann curvature tensor looks like. So therefore, the covariant derivative of the Riemann curvature tensor, covariant derivative of the Riemann curvature tensor, sometimes there's typos in this that I just overlook, is going to look like this. So this is going to look like this. So this is the derivative symbol for our Riemann curvature tensor. Another way of writing this is with the semicolon. So the semicolon just means derivative with respect to the sigma index. And what we can do now is we apply that sigma, right? So d sigma and d sigma, and the rest is just the Riemann curvature tensor. And we're going to do this cyclically. And what I mean by this is we're going to permute these guys right here. Okay, notice how these guys remain constant throughout the whole thing. Okay, so we're going to permute this guy such that I always just like thinking about this as sigma is going to travel this way. So here it is over here, and then here it is over here. You can see, I'll put a little dot under sigma. And then mu is going to travel in the same direction. Okay. And then I'll do blue for nu is going to travel in the same direction as well. And we really just rename all the indices, right? We're renaming all the indices in all of these guys. This guy got kicked, these two guys got kicked out for some weird reason, but they're still there. It's just when I was typing this up, it wasn't letting me do that. But nevertheless, when we add all of these up, we see that a lot of things are going to cancel. Everything's going to cancel, right? So sigma nu, right? And then nu sigma, and then nu mu, or mu nu, and then mu nu. Right, so these guys will cancel, these guys will cancel, these guys will cancel. So we get 0, and so adding everything up gives the Bianchi identity. So this here is the Bianchi identity. What it says is that the covariant derivative of the Riemann curvature tensor with respect to the last two indices, those are the two input vectors that you use to define the direction, and the direction of the derivative you're taking it in, goes to 0. Now, what does this mean? Well, before we ask that question, what I want to do is I just want to recall all the identities associated with the Riemann Curvature Tensor. What we said in the last video was this, okay? By permuting two indices in the Riemann Curvature Tensor, we get two anti-symmetric permutations, and we get one symmetric permutation. And then permuting three indices, we had this identity we found out last time, and now we're adding this identity. We're looking at derivatives now. Okay? So these are all of this is exploiting the Riemann curvature tensor and its symmetries to its maximal power. Okay? So now we want to talk about what exactly this means physically, because we're starting to merge into the area of sort of more physics and less math. And what we're going to be doing is we're going to find out that this implies something very physical. Okay? And what this implies is that if we start with the Bianchi identity, this is what we just had, we multiply both sides by the metric, it'll give us this. Okay? We see sigma gamma, or gamma sigma, gamma sigma, gamma sigma. Right? Mu alpha, not alpha, mu nu, alpha mu, right? Alpha mu, alpha mu, alpha mu, and then beta nu, and beta nu. Here's our beta, and here is our alpha, and gamma sigma. Here's our sigma, and we can do this for the other one, right? So here's our sigma, here is our alpha, and our beta is right here. Okay, and then same thing over here. All right, so we have our alpha, our beta, and then mu nu. Right, so we actually have mu and nu. So we multiply both sides by a metric. When we multiply this side by the metric, that's just 0, right? That's just going to be 0. So we can condense things down, right? Because we have alpha, beta, mu, alpha. This gets condensed down to the Ricci scalar. And then here, alpha, beta, this stays the same. And then this guy's going to stay the same also. We can then, so mu alpha, so we're permuting indices here, right? We have mu, sigma mu, alpha, beta. Remember, that was a symmetric permutation. Same thing here, symmetric permutation. Okay? And then we have anti-symmetric permutations. Okay, so we get, which is where these minus values come from. So we're left at this point. We didn't really do anything, right? We just multiplied by the metric and then permuted some. All right. So, but now we're going to take this equation here, and we're going to say now, using the Ricci tensor definition, we can actually now mu, or alpha mu. Here's alpha. So alpha is going to get raised to a mu, beta is going to get raised to a nu, and so we get, so we can actually raise things, right? So sigma beta, here's sigma beta, so mu and alpha, so alpha is going to contract out, and you can see how this is working, right? So we have, and then beta nu, gamma sigma. So gamma sigma stays and beta mu stays. So what we're doing is we're contracting out G alpha mu, right? And here we're contracting out G beta nu, okay, to get this. And then here we see that we're now contracting sigma and sigma to raise to gamma, beta and beta to raise to nu, and we're doing the same thing here. So again, we're contracting indices, we're playing with indices. This is all we're doing. We're getting to this point, okay, because this point here, nothing changes. This is now we're summing over indices here, right? So these are just dummy indices, so we can swap those to sigma. Again, dummy indices, we'll swap these to sigma. So nothing has changed. This is the same thing as this up here, which is, and we started all this with the Bianchi identity, right? So nothing has changed. We just multiply both sides by something, and then we're swapping around indices. Okay? But now, this is where things get quite interesting, because we see now that we have this guy, right? So this guy right here is right here. These two guys are the same, so it's minus 2 of them, all right? But we now have, this is a derivative sigma of this object in here. Okay, we've just taken the derivative sigma out, right? Because it was common in both terms. And then we get to this point here. Well, if you recall, we talked about this being the Einstein tensor. The Einstein tensor, again, was this object that identified curvature in a plane on an n-2 dimensional plane on our manifold of dimension n. So you take a manifold of dimension 4, for example, and G alpha beta is going to represent the R alpha beta mu nu curvature on a plane of 2 dimensions. Right, so these two guys are inherently linked, which is what we talked about last time. One's just a projection of the curvature onto a lower dimensional plane that's tangent to the manifold, and it's by 2 dimensions lower. Okay, but now what we're finding is that this G alpha beta, this curvature, has 0 divergence. Okay, this is 0 divergence. It's this claim right here, and this claim came to us from the Bianchi identities. Bianchi identity, and if you recall, the Bianchi identity was nothing more than taking the derivative, multiple derivatives of the Riemann curvature tensor. Right, so the divergence of this tensor is 0. All right, that's the claim. The Bianchi identity of the Riemann curvature tensor is therefore equivalent to the statement that the divergence of the Einstein tensor is 0. And this is critical. This is a critical piece in our story of GR, because what we're going to find is that the divergence of our tensor, our stress energy momentum tensor, is going to be the same thing. Gamma sigma equals 0. Okay, and Einstein's claim is that if this is true for stress energy momentum, And I found out that this is true for my Einstein tensor. Well, this has two indices. This has two indices. They must be equal. That was Einstein's fundamental claim about the universe and how gravity played a role in curvature as tensors, which are objects that transform in unique ways, having divergence of equaling to zero. So we've sort of gotten to a point now where we can say that G, I'll keep it my indices, gamma sigma is equal to T, or proportional, I'll say proportional to T sigma, or gamma sigma. And what we want to do here is put a constant to make them equal, because we know that they're not directly equal. They have to be scaled up by some constant, right? But this was Einstein's claim. Fleshing this out, we get the formula that R gamma sigma minus 1/2 gamma sigma R equals, I'll say kappa, which is our proportionality constant, T gamma sigma. This is the Einstein field equations. We've derived the Einstein field equations from the Bianchi identity, which came from just derivatives of the covariant of the Riemann curvature tensor, which is just derivatives of the connection, which is just derivatives of the metric. So with that being said, I will, if you like this kind of content, make sure to hit that like and subscribe button, and make sure to go into my Patreon page if you want to see notes on the topic. In the next couple of videos, we're going to dive deep into the stress energy momentum tensor. We're going to be talking about it also within the context of electromagnetism and how stress, energy, momentum, and electromagnetism curve space. Okay? So I will see you guys in the next video.